we've been working on long division and synthetic division, and it does have uses when dealing with rational expressions, graphing, and that sort of thing, but it can also be really useful in finding roots. So you guys are expert at finding roots of quadratics, factoring, graphing, um, completing the square, quadratic formula, all of that stuff. But if we jump up from a quadratic to an x to the third, I don't even know how to factor an x to the third unless it's that really special case where it factors into um, two binomials, which is something we did not long ago. So apparently there is some way to factor x to the third equations, but it must be so complicated that mathematicians decided not to do it because the only thing I've ever seen is something similar to what we're about to do. So we're working on 294, 1 through 18 all. So if you look at page how far back is it going to make me go? Okay. So if you look at page 282, example 2, we have an x to the third equation, and it says, determine whether x plus 2 is a factor. If so, factor completely. So we have this polynomial, and we want to know, does x plus 2 go into it? And if it does, then we know one of the factors. How many factors does this have? 3. So if we have an x to the third and we find one factor, it will simplify to a quadratic, and then we can use our factoring skills of quadratics to find the other two. So if the factor in the denominator is x plus 2, what do I put in the synthetic division box? -2. And then I line out the coefficients, 1, -2, -5, and 6. Drop the 1, multiply, we get -2, which is -4. Multiply, and we get 8, which is 3. -2 and 3 is -6. And my remainder is 0. What does that mean? It is a factor. So one of the three factors is x plus 2. Okay, what are the other two? Well, I take what's left, and I turn it into a quadratic, x squared minus 4x plus 3. Does x squared minus 4x plus 3 factor? X minus 1 and x minus 3. So x minus 1 and x minus 3. Okay? So if you look at 294, number 1, it's kind of like that, just a little bit different. It says, given a real zero of the polynomial, determine all other real zeros, and then write the polynomial in terms of a product of linear and or irreducible quadratic factors. So it tells us this graph hits the x-axis at 1. Find the other place it hits, and then list all the factors. So if this is 1, what do I put in the synthetic division box? 1, because roots go in the synthetic division box. And what do you notice about that cubic equation? It skips the x squared, so we need to put a 0 in its place. So 1, 0, -13, 12. I already know what the remainder is going to be. It's already going to be 0, because it told me in the beginning that is a root. And whenever you synthetically divide using one of the roots, you'll get no remainder. So 1, 1, 1, 1, -12, -12, 0. So I knew that was going to happen. Why did I bother to do it? I needed this equation here. So the first factor would be x minus 1. And the three roots, one of them is 1. And now over here, x plus 1, x squared plus 1x minus 12. Does that factor? So x plus 4 and x minus 3. So that's what goes over here. X plus 4 and x minus 3. And what are the other two roots? 3 and negative 4. Pretty simple, right? What if this quadratic does not factor? Then the roots are irrational or imaginary. And we would just, if you look at the instructions, it says, represent the factors as product of linear factors or irreducible quadratic factors. Yeah. It says determine all other real zeros. So it wants, if this doesn't factor, it wants you to use the quadratic formula to find what they are. But over here, you don't need to list them this way. You would just list this. So if you had x minus 3 and something like x squared plus 2x plus 7, which doesn't factor, you still need to find the roots. So the roots would be 3, and then you'd use the quadratic formula to find what they are. So like 6 plus or minus root 2 over 8 or something. But when you list it as factors, that is as simple as that factor gets. Okay. So look on the next page. We'll do 5. Number 5 is next to the fourth problem, but they give us 2 zeros. What should I do here? Okay, and then what? So you're going to either divide twice using synthetic division, or you could combine these into a quadratic and do long division. So it would be, so the factors are x plus 3 and x minus 5, and that turns into x squared minus 2x minus 15. So I either divide synthetically with negative 3, write the new equation, and then synthetically divide again with 5, or I can long divide with this and just do it once. I personally prefer synthetic division twice versus a lengthy long division. So negative 3 goes in the box. 1, negative 2, negative 11, negative 8, and negative 60. 1, negative 3, that would be 6, 4, negative 12, so negative 23. What is that? Positive 69. Uh-oh, did I mess up? Oh, I did. Sorry. 1, negative 3, negative 5, and then that's 15, so 4, negative 12, negative 20, and 60, and that gives me the 0, so I know I did it right. And now this is an x to the third equation, so I'm going to synthetically divide it by the other root, 5. So, drop this down. 1, 5 gives me a 0. 0, 4, and then 20, and that gives me 0. So my factors are x plus 3, x minus 5, and this is x squared plus 4. Does x squared plus 4 factor? No, it's a sum of perfect squares, not a difference. If it was x squared minus 4, then the factors would be plus or minus 2. But if it's a plus, then the roots end up being plus or minus 2i. So my roots are -3, 5, and plus or minus 2i. And you can see that by setting this equal to 0. Subtract the 4, and I get x squared equals -4. Square root x equals plus or minus 2i. And hopefully that's as complicated as the imaginary roots go. If the people who wrote this book were intelligent, which I'm not saying they were, that's as complicated as the imaginary roots would be. Okay. So, what if they don't tell me what two of the roots are? So if you look at number 11, we have an x to the 4th, and eventually we're going to be finding all of the roots. But they didn't tell me any of the roots to start with. So what if I had to guess? Is there any number that would be a better guess than any other number? 1 is always a decent guess. Would 0 work in this case? If 0 works, then the constant term is 0, right? In order for a polynomial to hit 0 on the x-axis, it also hits it on the y-axis. And that means if you plug in 0 for x, you get 0 for y. And if I plug in 0, 0, 0, the only way for that to work is if there's no constant. So if you don't see a constant, 0 is guaranteed to work. Okay? Can you think of any numbers that won't work for sure? -8 won't work. Why? Well, if this polynomial is factorable, it was created by multiplying binomials together, right? So if it factors, and it might not, but if it does, then it had 4 linear binomials multiplied together. And all of these would have an x in them. Would they be bigger than x? I mean, would it be like 2x or 6x or 8x? How do I know there are no numbers in front of the x's? If you look at the leading coefficient, it's 1. That x to the 4th is created by multiplying all of the x's together. And if the x to the 4th ended up having a 1 in front of it, then the only way to multiply 4 numbers together and get a 1 is by multiplying 1 4 times. So what does that tell us about the rest of the polynomial? Where does this number come from? It's the y-intercept, but when I look at all of these linear binomials, where does the n number, where does the constant come from when you're multiplying binomials together? It's the product of all of the constants, right? So whatever this is, times whatever this is, times whatever this is, times whatever this is 4. So why will -8 not be in one of those boxes? It's bigger than -4, or than positive, it's bigger than 4. Now, signs are a little bit confusing, because if this was a -1, and this is a +1, and this is a -1, now I have a +4, and I could times it by 4. So I could have -1, -1, +1, +4, and that would work. Or they could all be negative, or they could all be positive. So signs are a little bit tricky. But as far as factors go, it's pretty easy. The only possible numbers to go in here, 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 or here would be 1, Well, plus or minus 1, plus or minus 2, or plus or minus 4. How come? Those are all factors of 4. So those are the only possibilities. Okay? It can't be anything else. It can't be a 5. Well, what if this one was 5, and what if this one was 1/5? If that's a 5 and that's a 1/5, they would multiply and be a 1, and then I could times it by 4. But if this is a 1/5, then that would not be a 1. Right? The only way to factor a quadratic and get fractions is if you have a leading coefficient. Okay? So somewhere back here, they're going to have something called the rational root theorem. Oh, wait, we got to do one more thing. All right, so let's look at 17. What are the possible roots for 17? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Now, that takes care of the 20. Okay, 21 won't work because 21 does not go into 20. But this one has a leading coefficient, right? So it is possible for one of these factors to turn into a fraction root. But what is the only possible denominator for those fractions? The factors of 5. So you could have 1/5, or 2/5, or 4/5. What about 5/5? It's 1. It's already listed. So the rational root theorem says, for any polynomial, the only possible rational roots. What does rational mean? A decimal that ends or repeats, or more simply, a fraction. If the answer to this is a fraction, the only possible fractions are the factors of the constants, or the factors of the constants divided by the factors of the leading coefficient. So plus or minus 1/5 is an option. Plus or minus 2/5 is an option. Plus or minus 4/5. And what about the rest? 5/5 is already listed as 1. 10/5 is already listed as 2. And 20/5 is already listed as 4. So here's how they explain it, which is not going to make it. You know, people who write textbooks are really annoying. So if you look on page 284 at the rational root theorem, the rational root theorem says for any polynomial, so we have a first term and a last term that has integer coefficients. So all of the coefficients are integers, right? So 1.8 doesn't work. Pi doesn't work. But if there are integer coefficients, 1, -3, 7, then the rational zeros are any integer factors of the constant divided by any integer factor of the leading coefficient. Okay? So really, you don't need to know anything about the polynomial except the first term and the last term. Where do all the middle terms come from? When you multiply it all together, they get mixed together and you combine like terms. But the first term is a product of all of the first numbers, and the last term is a product of all of the last numbers. So if I had 6x to the 5th, dot, 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 15. What are the possible fraction answers to this? Well, you do all the factors of 15, so plus or minus 1, plus or minus 3, plus or minus 5, and, oh, plus or minus 15, thanks. And then you divide all of those by all of the factors of the leading coefficient. So this is 1, 3, 1, 1, 2, 3, or 6. Do I need to divide by 1? No. I do need to divide by 2. So plus or minus 1 half, plus or minus 3 halves, plus or minus 5 halves, plus or minus 15 halves. Do I need to divide by 3? For some of them I do. I need to divide the first one by 3. I don't need to divide the second one because it's just 1. Plus or minus 5 thirds. And I don't need to divide 15. Do I need to divide by 6? So I need 1/6. I don't need to do 3/6 because that's 1 half and it's already listed. Plus or minus 5/6. What about 15 over 6? So 15 over 6 simplifies to 5 over 2, which I already have. Okay? So on that last set, so on 11 through 18, you just list the possibles. What could the answers be? And then after that, it's just sort of a guessing game. Which one works and which one doesn't work. But there's more I'm about to teach you on how to make better guesses. I mean, we have, so 8, 16, 32. We have 32 possible rational answers. Is it possible for none of them to be right? Yeah. They might all be wrong. This quadratic might have, well, one of them has to be right, doesn't it? No, that's not true. What if the answer is pi? Well, it's odd, so it does have to hit the x-axis in one place, but does it have to hit the x-axis at a fraction? No, it could hit at an irrational number, in which case none of them would be right. So it is kind of a guessing game, but we don't have to guess today. All you have to do is list the possibilities. Okay. No, so positives and negatives will come into play later, but as far as possibilities, it's always plus or minus. We'll deal with negatives later.